Hi, my name is Brian Caffo, and this is the lecture on T-confidence intervals in the statistical inference class. This class is co-taught with my collaborators Jeff Leake and Roger Peng. We're all in the Department of Biostatistics at the Johns Hopkins Bloomberg School of Public Health. Okay, so in the previous lecture, we discussed confidence intervals using the central limit theorem. And this lecture will discuss some methods for small samples, notably Gosset's t-distribution. And so to discuss the t-distribution, we have to discuss the so-called chi-squared distribution. And we'll use this kind of following procedure to create a confidence interval. We'll create a statistics that doesn't depend on the parameter of interest called a pivot, and then we'll solve for the probability that that pivot lies between the bounds of the parameter. And I think for many people, the mathematics of this might be a bit above what's intended for the series. I just wanted, for those of you that are interested, to show you that there's a kind of this common framework that keeps popping up. There's a reason for it. It's not that just people are refiguring out the same thing every time. The chi-squared distribution is a very important distribution in statistics, and here's one of the ways in which it pops up. Suppose that S squared is the sample variance from a collection of normal data, IID normal data. Then if you take n minus 1 S squared, right, which remember is actually just the sum of the squares, we've gotten rid of the denominator, and then we divide that by sigma squared, that follows a so-called chi-squared distribution with n minus 1 degrees of freedom. So a chi-squared is a skewed distribution. It has support from 0 to infinity. The mean of the chi-squared is its degrees of freedom, and the variance is twice the degrees of freedom. So let me just mention that you can use the chi-squared to create a kind of quick confidence interval for the variance. So here we have the chi-squared distribution. Imagine if you grabbed this point and this point, x 1 minus alpha over 2 and x alpha over 2, so that alpha over 2 lied here and alpha over 2 lied here and 1 minus alpha lied there. Okay, so for example, alpha could be 0.05 and then you'd have 95% lying in the middle. By the way, because it starts at 0, it's not like the normal case. This isn't like the negative of this other one. They're two different numbers, a number close to 0 and a number bigger, a bigger number. Okay, and so because this guy is chi-squared, it's the probability that it lies between these two numbers is 1 minus alpha, right? It's this shaded area. We can just work around with that equation and get that sigma squared lies between these two things with probability 1 minus alpha. So that's just a 1 minus 100 1 minus alpha confidence interval for sigma squared. It's not a terribly good confidence interval for sigma squared, but it's a quick one that you can do, and it's a if you want an interval for sigma, you just square root the endpoints. But the reason it's not very good is it relies, this interval it relies very heavily on the normality, and so you might want to bootstrap or something else to get a better interval. So yeah, let's just do an example. But it's quick, right? The bootstrap is slow, and this is super fast. It doesn't get any faster than this. So here's x is the sun's height from this father-son data from the using our data set Galton. S is the standard deviation of x. N is the number of observations. Then here is my confidence interval, just plugging in the normal way. Notice I'm grabbing the 97.5th and 2.5th percentiles. Make sure I did the degrees of freedom right. Make sure I squared, so I'm putting the variance in it. I'm rounding it to 3 decimal places. It gives me my interval from 2.7 to 2.9. So that's an example of creating that interval. But one of the real reasons we're going to talk about the chi-squared distribution today is to come up with a far more useful interval, which is the t-interval. So it was invented by this guy, William Gosset. Seeley was his middle name, William Seeley Gosset. And he published it under the pseudonym Student because he worked at the Guinness Brewery in Ireland, and the Guinness didn't want him publishing under his real name because they didn't want to give away the information that they had, kind of academics and researchers working for them. Kind of neat little fact. So the student's t-distribution was invented at a brewery. Anyway, the t-distribution looks like a normal if you were to like kind of squash it down and the sort of juice of it was kind of flew out into the tail. So here's a normal, and then the t is like a squashed down version of it. It's indexed by degrees of freedom, and as the degrees of freedom get bigger, it becomes more like the normal distribution. Okay, so how do you get a t distribution? You take a standard normal and divide by the square root of a chi-squared divided by its degrees of freedom. The two things have to be independent, and if you do that, you have just created a t random variable. So let's show how it comes up in this case. So we know that if we have normal data, then x bar minus mu over sigma or square root n is standard normal, and this doesn't depend on the central limit theorem. If they're normal, then that's exactly standard normal, not approximately. And then b, we know that n minus 1 s squared, so we know that n minus 1 s squared over sigma is chi squared, so that divided by n minus 1 and then square root is the square root of a chi squared divided by its degrees of freedom. Okay, so, and that works out to be s over sigma. Okay, so if we take this guy, which is a z random variable, and divide it by this guy, which is the square root of a chi squared divided by its degrees of freedom, we get x bar minus mu over sigma. And notice it's just the same thing, x bar estimate minus what it's estimating, estimand, divided by standard error, only now it's the estimated standard error, where instead of sigma over square root n, we have s over square root n. So it's good because it figured out a way to get rid of the sigma, which we don't know, and replace it with s. And that follows a t distribution with n minus 1 degrees of freedom. Cool. Then we can go through the same game that we did before and create a confidence interval for mu. So if we take and get the t distribution's centered at 0. So if we get this t quantile, and then that's the negative t quantile, that's the negative of that number, so that there's alpha over 2 up here and alpha over 2 down there and 1 minus alpha in the middle, the probability that this guy lies between them should be 1 minus alpha, right? Just because it follows a t distribution, and that's just the definition. And this is a lot of extra notation, just saying it's n minus 1 degrees of freedom, and then this is the negative one, and then this is n minus 1 degrees of freedom, and then this is the positive one. And then if we manipulate this equation, we get that mu lies between these guys with probability 1 minus alpha, so we call that guy the 1 minus alpha times 100% confidence interval for mu. So notice it's the exact same interval as the central limit theorem derived interval that we did a lecture ago. The only difference is instead of the normal quantile, we have a t quantile. Instead of sigma, we have s. Now it turns out if the central limit theorem still works if we have s there, but n has to be large, whereas this interval works, presuming our assumptions are correct, if n is small. Okay, so some notes about this interval. The t interval technically assumes that the data are normal, but it's very robust to the normality assumption. Whenever the distribution of the data is roughly symmetric and mound shaped, the t interval is going to actually work pretty well. And then paired observations are obviously often analyzed using the t interval. If you just take a difference, so it seems like you have two observations, but if you have a person measured at baseline and a person measured 1 year later, and you have a bunch of measurements like that, then if you just take the difference between the 1 year measurement and the baseline measurement, then you just have one number per person. That's often analyzed by a t interval. For large degrees of freedom, t quantiles become the same as standard normal quantiles. And so, kind of the safe thing to do is just always use the t distribution, because if n is big enough, then it'll just convert it into a normal for you. For skewed distributions, kind of the spirit of the t interval is violated. Maybe you might want to consider taking logs of your data or doing something else. And then for highly discrete data, that's another thing. There's other intervals that are available and maybe a little bit better. So here's Gossett's original sleep data, and it was analyzed in this journal Biometrica, which was founded by Francis Galton, and it's a very old journal. And at any rate, it shows the increase in hours slept for patients on 2 sleeping drugs. R treats the data as 2 groups, but I went back and read Galton's paper, and he treats them as paired. So here's the data. You can look at it. So I create the two groups like that from 1 to 10 and 11 to 20, and I create the difference. Mean is the mean difference. S is the standard deviation of the difference. My n is 10 in this case. And then here's my confidence interval, which is what I really want to show you, which is just quickly how to create a t-confidence interval. Mean plus or minus t quantile, relevant t quantile, times the standard error. We get that interval, and of course, because this is such an important procedure, there's obviously an R function to do that. It's called t.test of the data, the differences. If you can do $confident, we'll just grab the confidence interval. If you don't do $confident, it'll print out a bunch of other stuff, including the result of the hypothesis test. And of course, we get the same number. So that's the t-interval. If you know the central limit theorem interval, you should switching to the t-interval should have introduced absolutely no new confusion. The benefit of the t-interval is that because of the t's wider tails, right? Here's the normal distribution. Here's the that's horrible. Let me do that again. Here's the normal distribution. Here's the t distribution. Because the t distribution is flatter, its quantiles are further out in the tails. That results in a wider interval. It's a more conservative procedure than the central limit theorem based interval, and it generally performs well. It's highly robust to its assumptions. So it's a very good interval, and it's probably maybe the single most used statistical technique is the t-test and the t-interval.